Alaikum. Today experiment is lamp capacity model. So it's unsteady heat transfer. So if I have a ball, this ball have M, mass M, and Cp, specific heat and surface area, AS, and initial temperature, Ti, and then this ball I decided to fall it inside a tank that has a fluid of temperature T infinity, and heat can be transferred by two things: by convection from outside from the fluid to the body, and then by conduction inside the body itself. So to determine the temperature of the body at any point, it will be a function of time and x, the position. So as you can see, this is maybe a little bit complicated to include or to have both of them. So the lamp capacity model is a way to ignore the effect of x, so it can assume that the temperature in the body is just symmetric. Okay, so all points here have the same temperature. So then the temperature will be only the function of time. So lamp capacity model assumes that the temperature variation within a mass of conducting solid can be neglected in comparison with a temperature difference between the mass and the surrounding fluid. In other words, we can say that the resistance to the heat transfer within the mass is negligible when compared with the resistance to the heat transfer with the surrounding. That means the resistance here is almost zero or almost negligible compared to the other one, to the surrounding. That's why I have only gradient in heat transfer due to the fluid. Once the temperature reaches the surface, because it has high conductivity, or we can say the resistance is very small, okay, so then the temperature, once it reaches here, it will reach every way inside the solid, so it will be identical, almost identical. So we said resistance to the conduction, L over K over 1 over H, will be very small. The scientists say that this value, we can rearrange this value, so it will be here L, and then H will be here, and K will go down, and we will call it Biot number. So HLC over K should have a very small value, and they nominated 0.1 as a value that you should have, or less than this value. So what is LC? This is characteristic length of the body. It's different from shape to shape, but to calculate it, you have to, it's a volume of the shape divided by area. So volume by area will be the characteristic length of the shape. So now the temperature will be a factor of time only. So we can say that the gradient of temperature, or the difference in heat, internal heat transfer in the body, is only due to the convection. Why? Because we already cancelled the effect of conduction. Okay, so minus mCp, the term of dt over d time, will be HAS T initial minus T infinity. So m, as you know, it's equal rho times volume, rho v. So minus rho v Cp differential temperature differential time equal HAS Ti minus T infinity. So I can rearrange this equation. So I will move the temperature part here and move this part to other side. So it will be like this. Why I put it like this? Because I want to integrate. So I will integrate from T initial to T, and from T from 0 to time. Okay, so by integration I will have ln T minus T initial over Ti minus T infinity, and here I have a time. So if I take the exponential, it will be t minus ti, ti minus t infinity, exponential minus has rho vcp times t. This term has over rho vcp, we can call it b. Okay, b. So we call this b. So b will be has over rho vcp, and it's called or known as time constant. Okay, time constant because it's 1 over time. So 1 over time times time, so they will cancel each other. Okay, so I have here I have dimensionless group, and here also I have dimensionless group. Okay, so okay, what is the importance of 1 over t? Sorry, the importance of b or the time constant. If I calculate it, I can determine how fast my shape can go quickly to equilibrium. Okay, so the biggest value of b, that means the shape can reach equilibrium quickly. So for example, I have this shape. Okay, this is for two curves. This curve, the blue one is larger than the b is larger than the red one. So as you can see, this is t initial and this is t infinity, and this is the curve represent time by time. So as you can see, b here reach quickly to the equilibrium rather than the red line. So okay, how can I use or apply these equations? I can either use the len or use the exponential one based on what value I want to determine. If I'm interested to determine the temperature, so I can use the exponential one. So it will be temperature equal Ti minus T infinity e powered minus Bt plus Ti. So this is to determine the time at the temperature at any time. So if the time is given, okay, and you want to determine the temperature, so you can apply this equation. The other equation, I can use it, the len one, to determine the time. Okay, so for example, if you want to calculate the time required to reach certain temperature, then I can apply the second equation. Again, okay, byte number. We said byte number equal HLC over K. So K of the metal is known, and LC characteristic length I also can determine based on the shape, and we have H. Okay, H is for the fluid. Okay, so how to determine it? It's difficult to determine. It's a given, okay, or calculated empirical, so that's fine. But in experiment, how to determine? Okay, so you want to find a proper way to calculate H. Okay, so now we can conduct our experiment, okay, and calculate the length. If I, for example, if I drop a ball in the water and then I calculate T minus, I have initial, okay, temperature and infinity temperature, and I have T, okay, that's recorded every time with T, okay, the temperature is recorded with time. So then the rho is known, T is known, T is known, and N is known. So I can calculate H experimentally. This is concept. But this concept is not accurate. Why? Because I calculated this equation, okay, this H, based on I suppose that the conductance is negligible. Okay, because this equation is based on conductance is negligible. Okay, and the temperature is factor only, time only, without position. So how to solve this? So now let's try to solve it now. Now we said then T minus Ti over Ti minus T infinity equal minus H times As over rho Vcp times. Okay. Now as we said before, A over V, we said V over As is the characteristic length, if you remember. V over A. So this equation will be minus H over LCCP times. So I rearrange it to the characteristic. So now if I multiply this equation to precision 1, so it will not affect factor. So I will multiply by the distance to the conductor, K over LC, divided by K over LC. So this will be 1. So if I multiply here, it will not affect the running equation. So this one also equal to, like, if I multiply by KLC over KLC. Okay, so let's see what will happen if when I included the effect of the conductance here. It will be HLC over K times K over rho LC again. So we have two LC from here, CPT. So the red one is from the previous equation, and this one, the blue one, from the new values. So now let's see this. It will be the LC times LC will be LC squared. Now this term HLC over K is what? Is the Biot number. And K over rho CP is what? Is the thermal diffusivity. And if I divided thermal diffusivity by squared LC, so it will be something called Ferrari number and T. Okay, so we have here, okay, this length T minus Ti over Ti minus T infinity will be minus Biot number times Ferrari number. So now if I plot these values against Ferrari number, the slope will be Biot number. So if the Biot number is larger than 0.1, okay, that means this shape is not, we can say, is not a Biot number. It's not a lambda capacity model. And if it less point number or less, then we can consider this shape is lambda capacity model, and we can calculate H from the Biot number. So here we can say that H equal Bi times K over LC. And then we can determine the temperature. Okay, so we have the temperature curve, that's accurate curve, or the we can say experimental curve, and we can have one like a model curve. Okay, so we can have 2T, this one for the experimental curve we obtained from the experiment, and we can calculate another temperature, use this equation and compare between them. Okay, so this is the calculation of the experiment. We have a time in second, and we have the time experiment. We can determine the temperature profile, okay, Ferrari number, temperature theoretical, okay, and the error, okay, between theoretical and the temperature experimental. Okay, and this will be the raw data for my shape, like a density, like diameter, R, like surface area, volume, specific heat, diffusivity, conductivity, characteristic length, Bi, H, B. So all these are required for calculation. We have here you can see here dimensions. Okay, for the cylinder we have sphere and cylinder and cube, okay, or slab. Okay, and this is the experiment. So here we just drop the shape here, okay, and from here we can see the temperature. So this is a screen you will get. So we have, for example, the material is a brass. Okay, thermal conductivity is shown, thermal diffusivity also is calculated for you, density and specific. So no need to calculate anything. Okay, and we select the correct shape here, and then we can press run. The temperature will record it, and then we can export it in an Excel sheet. That's it. Thank you so much. Assalamu alaikum wa rahmatullah.